Welcome everybody to the second part of Turing Complete, where we will finish the campaign. We will also get started right away with using an instruction of your computer. Read the input twice and exclusive or the two values together. Does my ALU have a XOR unit? Let me take a quick look. Please show me my ALU. No, NAND or. I mean, I could build XOR, but we can also pretty well just build our own real quick. Yeah, let's do that, I guess. Yeah. Let's populate with 1 and 2. Then think about it real quick. Exclusive ORs when only one of them is on, which is an OR and an AND. Do we have an OR yet? I don't think so. So we go to instructions, compute OR is a 64. And then we do a rec3 to, let's say rec4. And we do have a rec5 for the other one. Though we don't actually need it. In which case, now that we have OR in rec3, let's do rec3 to rec4 to save it. Then we do get an AND, which I do have to look up to. Which is a 67. So we will enter that. Now we have an AND in register 3. Let's put that in rec 2. Let's put our AND in register 1 then. Which should pretty much be this. It is, we checked that just now. Now we can just do another AND. And then we just output it and it should work out alright. Let's see, where are we going wrong? We do have those in here now. 119, 21. go into the ALU and we do get 140 out. Let's see what we're doing wrong real quick. 64 should indeed... I should stop clicking on that. .64 is indeed an OR. If we do type it in here real quick, an OR would give us this pattern. Okay, I see where my mistake is. We do need an AND instead of this one, which is a 65, and that should hopefully fix it. Now 64 is an OR, let's comment that. 65 is an AND. I do however need an AND, which is... No, I do have a 65, which is an AND. Windows, please don't make this any more difficult. This one is an OR. This one is the output of an AND gate. And this one is the output. We do want an AND gate here, AND gate here. Yes. And we are done with XOR, which I did just do through combining logic gates in code. Now we do need an equal. Do we have an 8-bit exclusive OR? No, we do not. However, we did just do it in code, so we do need an AND, NAND, and an OR, if I remember correctly. Let's just take a look at our code again real quick. We do have an OR and AND, and then we put that in an AND. We will basically do the exact same thing here. Now this will give us for each of them Give me a second, we split this byte now. This will now give us a signal if one of the bits is different. And we just have to combine them now and see if any bit is different. So we should use an OR gate. Actually, multiple of them. And a two-gated OR gate. Connect them up real quick. And that should pass. I do, however, need to negate it real quick. Now it should pass. And it works. Now we do have an equals block. Next we will exclusive ORs 2 bytes bitwise. But we did just do an exclusive OR, so that would have been handy to just have. Where we will just get a NAND, an AND, and an OR again. And repeat pretty much what we just did. Still the same we did in code earlier. Next, create a circuit that outputs green when the first input is less than the second. Signed bytes, okay. First is less, okay. In that case, let's see how do we want to do it. Do we have an add? Yes, we do. Let's just add them together. Split it real quick. Now this is basically our signed byte. And if we subtract a larger number, this will be true. But I will also... Actually, let's just connect that real quick. Sadly, the game is having a few problems because Windows doesn't like me. Zero is... Yes, it is. I see. Do we have... Yes, we do have one. In that case, let's just subtract them real quick and hope that fixes it, because I'm very lazy. Now -1 does carry this one. So we will just put that in an OR real quick and call it creative problem solving. Uh, 127. Okay. Sadly, this doesn't display negative numbers as I wanted to. Which in this case is just a -126, and which is indeed more, yes? Let's do it bitwise real quick. I hate this comparison, but well, that's just how it is. Now let's see, first this one and not the other one. Forgot, can't directly place it on the not. This will now handle negative numbers. And for this one I do now need to see which one has higher value. But for that I should be able to actually just use a regular division. At least I hope I will be. We do negate this one again and add 1. And if this one is, in this case, what do we have? Nothing that will really help us here. Except of course Windows really not being happy today. Let's give it a second and hope it doesn't crash my computer. Shouldn't be having problems either, but let me quickly try a fix. Let's see if it works then. We will just split this real quick. Okay, Windows, I see you're having problems, but I don't care. And now we just take a look whether the number's positive. And I probably need to do something else too, but let's just let it run till we run into an error. Signed bytes, right. We do have signed and no complement. In that case, I do only need to negate. And then we have and then we have this one. I did also forget to link that one. And let's not have it on when we have a negative number output. This is looking terrible already. And I am actually also back to really botching things. Now this is not less. And we do also already have the number input. Now is that less? We do the I should probably rethink that real quick. Yeah, let's rethink it real quick. Do we have a pen? No, we do not. Let me also quickly turn down the volume a bit. Now basically we do have numbers here, and if one is bigger, it is signed, which means this one is basically just means negative. Let me pull up a drawing program real quick. Let me quickly remember what my drawing program was called. And plug everything in. Almost ready to go. And a quick scene transition for you guys. Add source, do we have a simple window capture? Yes, we do. Windows doesn't like it, but I don't care. OBS doesn't like it, and that is really bothering me. Well, I do, however, need to start another program to enable drawing tablet real quick. Do we still have sound on stream? Let me check that real quick. We do still have sound on stream, which is really good. I do also need to increase OBS bitrate real quick. I see where a problem was. This one looks alright. Now I do just need to increase OBS bitrate real quick. Can I do that easily, or will we just hope? This will take a second. Maybe this will work out. Also, let me transition to drawing software. I did tell you to start driver for disconnected, okay. Why though? Let me fix that real quick. It's very connected actually. Should also be right driver, yes. More technical difficulties, okay, should only take a second. Seems to work fine now. It doesn't. Okay, let me restart the driver real quick. Let's start it again and hope Windows actually lets me use it. No. Please, pretty please. I really didn't want to have to do that, but well. Like this. Will you let me do it now? Yes. In that case my hub is probably broken. Okay, we do have 8 inputs here. And 8 here. This one is negative. And we are looking for A less than B. So we can pretty much already say if this and not this. As for those ones, we let me think real quick. If we just negate it, it doesn't matter, but we should only... If this is negative, we do not negate it, I think. So if neither of those are true, we can just negate it and move on. If both are the same, well, at least I got the driver working. Though I had to disconnect my mouse and now can't access the second screen to control the stream. Very unfortunate. And still need to increase bitrate a bit more. No, it really shouldn't be able to complain. I do, however, need to plug in the tablet again, which will take a second to start. Actually, do we have switches unlocked? Logic. Yes, we do have switches. Let me also drink something real quick. And also let me not bother with actually drawing it, because I just remembered we already built a fitting circle. At least for positive numbers. Let's go back to the game hand for this one. Level map. Actually, component factory, we should have it in our algorithmic logic unit. Don't we? No, we do have a compare circuit. Which, now that I think about it, I really do not want to look at. Curse you past me, this is looking really terrible. It is looking really terrible. Is it giving us any valuable output right now? I don't even know what this does anymore. We should. Let's just throw our heads against the wall until it works. They could have at least changed it to represent negative numbers correctly. I mean, this is a regular adder, but we can first of all add the numbers together. In this case, it gives us a negative number. And if the number is negative and this one is let's just tear this one apart and say if it's negative we already have one bit of our solution. Now if this one is negative, let's also borrow this one. Put a not in front. This should decrease our error rate. Is -1 less than? I mean, we do have an overflow, yes. Let's just put in an OR and see if it changes enough to make it working. Is 0 less than? No, it isn't. And those are equal. I mean, that one is changed easily enough. Really not the good looking kind of easy enough, but easy enough nonetheless. And let's also negate this. $77 And 76 is... Yes, of course, because we do have an overflow technically from positive to negative numbers. And Windows is not liking things again. Let's first just extract the sign of each number then. And let's choose a nice gray for the signs. Now if this one is negative and the other one is not, we can already say that the result will be true. I do, however, need to leave space for a wire here, which was our first step anyway. And actually already gets us very far. Now we just do have to need to do a comparison. In which case I will subtract those real quick. For which I do need to negate this one again. (76 minus 77 is... If we look at this... 76 again, that's... Let's just place it in a way that doesn't mess up the wires too much. Okay, our current problem, to reiterate, is we need to figure out which of those is smaller, which means now I do want to add them together. This one is 1 if it is positive. Just go with that real quick, where you still don't have any care for overflows right now. Let's also, just because I want to do another addition circuit real quick. Which we will pretty much use to do the same. But this time I will negate the other number. Now I'm pretty much just messing around again. Putting an OR here probably won't help me either. Yeah, because naturally this will always be an overflow. Windows doesn't really help today either. Now we already do check signs pretty well. We should, however, actually keep our lines connected, helps a lot too. Now, how do we successfully work with overflow? Let's see if we just randomly add the numbers together, which we already know isn't the solution. Let's subtract this one anyway. Actually, what did the level say? Signed bits, yes. I mean, technically, if I see this correctly, we can just throw the sign out and here we have a wonderful 127. I really don't want to be this guy, but that's compliment. Yeah, this is sadly not a neg. One, this is a 127. Which does mean to convert this correctly, we do need a negation real quick. And need to just enable carry-in. And now we do have the 1 in D. So it isn't signed at all, that's well, technically it is signed, but I did take the wrong assumption in how the number is represented. Did I? Well, I'm confused again, but that shouldn't stop us from actually solving this now. Let's just get a negated form of all the numbers we have. Now obviously to test if this is true, we can now just subtract. This is looking terrible already. Well, won't stop me though. Do we have an overflow? No. Yeah, Windows, I get it. You are not very happy about this. No need to remind me constantly. Let's just keep that real quick as a... Actually, I can probably just make a quick schematic for this, which we can't use here. Well, too bad. I do, however, also want to add this representation for problem solving. Yeah, I'm doing way worse than last time. Now let's take a look if I am allowed to. Now this works and is nice and all, but What if you just throw some odd choices at it instead? But also still, this representation will help us in solving it. Now let's do, however, keep those real quick. For negative numbers, this doesn't seem to... Yeah, can we start over? -1 less than 0, yes it is, because it is negative and the other is not. No, let's actually keep them. Let's take a NOT gate and just end them real quick because I'm lazy and want to see what the next will bring us. Now 0 less than -1. Yeah, we do need to compare positive numbers for this one. So we do actually need to take them apart real quick. Let's do that over here and over here. And then we should have one of those here. One input is this, the other one is this. And then we do have an add, please. And negation. Over here. Let's copy that real quick. Now we are choosing, in this case, the positive number. Let's do an AND here too. This will still not be the solution. And now we can also take those two. One AND, one NOT, and an OR. What else do we have? Now we do have different numbers. See if this is thanks Windows, but I would really like to see that right now. Which is a 1, which is off here. Let's keep that for now. And also get another byte splitter up here. Why ever I removed that one again. Now for this one we do have a negative over here. You know what, I will actually come back to this level after this one. Okay, let's start with unsigned, which is easy enough and will actually probably help us a lot later. In this case I can literally just subtract them real quick. And let's take that one, see if it's negative. Yeah, right, it's unsigned. Game, could you please? First input is less, yes. That was my mistake. Now 128. Let's start over. Is that less? No. Ah. Ah, yes. Wonderful day. Let's split them up for ease of looking at stuff. Helped a lot last time, might as well do it again. First less than second, okay. Actually, that is... We can just use this one for this. Let's take an and 2. I see where my mistake was now, yes. At least I say I am. No, it isn't. Yes, it is. Is 127 less than 128? Yes. Yes. Is 127 less than 128? Yes, it is. Let me see, do I actually have to... No, it isn't, but it... I see, yeah, I do need to get the highest one. In that case, let's get a decoder, splitter real quick. Can we turn this around by chance? Yes, we can. Still not helpful, never mind. Now we only want the active most significant bit. So we do have to extract that one real quick. We can technically do that with a lot of logic gates. Is there a mathematical operation we can do to keep only that on? Let's take a negation real quick. We do not have infinite access to that, okay. Now I do technically want to get one where all the other ones here are on. Which would be subtracting 1, I guess. Would it? For this one it would. Let's see. Put in a complement negation. I'm pretty cooked right now. We do have sign comparison. I want to do that after. Okay, first input less than second. Let's do it again. First input. And second input negated. And maybe. I mean, that won't be it, and my Windows is also struggling again. May I just skip through a few examples real quick, please? No? Okay. Okay, let's go back to fooling around till we find a solution. I mean, this tells us which bits are different at least. Yeah, let me just skip through a few. The main problem is that it doesn't give me a choice to get the most significant one. I mean, technically it is less, yes, and we should have a signal over there, yes. $127 should be less, shouldn't it? Ah, yes, of course. Yeah, of course, I did forget that one. Let's place a few ores. And a regular ore here. Okay. Now the problem is that we do not get the most significant one. Can we do that now? No, we cannot. Do we have single bit regular? No, we do not. I mean, I can extract the most significant bit, but it would be a real pain. My main problem right now is I am trying to get the most significant bit, which in this case would be what happens if I just do a bit shift. And then add negative. Fair. No, I didn't want to delete that. Now let's compare those two real quick. Actually, I do need to compare those two. $128, which is indeed the most significant one. And if we do AND gate real quick. Yeah, Windows, I get it, you really don't want to. And of course I also need to take it apart real quick. Actually, and yeah, I have no clue what I'm doing. Yeah, Windows, I get it. In this case, I do want this one, which should always be on. And want to turn off the others. I mean, actually, that's pretty fair. I am not disabling. Actually, why am I not disabling one? Let me think about it real quick. One should be off in this case. Okay, that explains my troubles. Next time I should indeed read more. Now we should also keep this on, because it will always be important. Then an AND, I guess. And that should actually be our most significant bit. Now there probably still is a mistake somewhere in there, but we will figure that out during the first test run, I guess. Let's just spam a few OR gates again so this works correctly. And that's right, that's right, that's right, that isn't. And 164 is not less. In that case, let's add some monitoring again. Here, here, and here. Yeah, here the most significant bit that isn't the same is indeed this one. And here it is. We do have one on despite only 4 having to be on. And to turn that off, I can just put an AND here maybe. Let's try real quick. Can 2 is off, so yeah, we are running into that problem again, where I do need to see if any of those are on too. Okay, let's go again. Actually, let's keep this so I do have stuff to work with. First off, we have 255 and 0 where everything is on, and 128 is indeed our most significant bit. Which means all the other ones are turned off. Here we do only have 2 on, and that turns the other ones off. Yeah, I probably just need to blow this up a lot. So if this is on, this is on. And then I just need a bunch of OR gates. Actually, let me just get a few AND gates and a few NOT gates. One, two, 3, 4, 5, 6, 7, 7. Select all of that, move it back a bit. And we do need a NOT gate for this one too. Actually, should I do this with AND gates? Yeah, I get it, Windows. Yeah, I do need OR gates too. Yeah, Windows, please do. Let's get another OR gate over here. And another OR gate. And another OR gate. And soon we will have the most significant bit all the time. Number 4 and another OR gate. And a NOT gate. And now that should only give me the most significant bit all the time. Seems like it, yes. Do I have that one here now? No, I do not. Well, that's a bummer. But with a bit of luck we can just copy this one and use it again. Copy this, go over here, and here we have it. Our most significant bit finder. Which means we will again have to get an exclusive OR. Next we just extract the sign from both of them. Put an AND in here too. Let's take this one. Mux if we can. Actually, let's all the output right here, so we can do less stuff later. Those are terrible components, by the way too slow. But I won't be designing anything proper today anyway. And another ore. Now this one should be pretty well known now. And let's see if this one is negative and this one is not, we switch it. But I do need this end. And do we have one for this? No, we do not. So let's get it wrong again the first try. This way around. Never mind. And because I am lazy, let's use this one. And let's do this one too. Splendid. Now we can finally move on. Create a device that saves the program output on even ticks and outputs both bytes on odd ticks. Saves to where? Okay, do we have a register ready? Yes, we do. Then let's get a counter ready. Great. an even tick output on odd tick. Don't, so we save like this. We put a not in here. And obviously we do also need switches real quick. Saves on uneven ticks, yes. Save on even tick, my mistake. And then we do it like this instead. Yes, it should. Ah, I see. Yeah, we do need the 8-bit switches. And I do need to keep those connected. Output both bytes. I am. Am I not? Outputs were 248 and 209. They should be, shouldn't they? Save byte, yes. Save byte, output both. Ah, that was my mistake. Never mind. Program, yes, we do know how programs work. Finally, it's time for you to start building. No thanks. 4 bytes per tick from program, okay. First opcode and operations take 2 arcs, yeah. Okay, fair enough. Okay, yes. Which architecture were we building again? I forgot. Lag, okay. No signal, no signal. We do have a program. Let's go through this again real quick. Upcode goes to our ALU. which we do have here. Then we do have memory. Six registers as usual. I take two arguments, yes. Okay, Windows, get over it already. And 3-bit decoder 1. We do have 6 here. Let's connect them real quick. Okay, we do have our ALU over here. And actually I should probably take our input as number 0. And then registers in order. Let's also take the input up here. And this will be our first. And it will also always be on. Then we need a second one. Same inputs. Can I actually just copy this one? Yes, but I do need to connect the wires again regardless. This is our second input. Actually, let's look at instructions again. Nice, I can set my own instructions. Okay, continue. Okay, yes. Counter to 6, output to 7, yeah. I do need a counter real quick. Increment by 4. Here we go. Counter was supposed to be 6, wasn't it? Yes. Now then we need to tear apart 1 and 2. This one gets over here. Then we will need a few OR gates, which are sadly rather large. Okay. Let's repeat that with the other one. We do need an OR here too though. So right now both are selecting that one. And now for an output we do have this one. And we do also need another output selection. This output, this one, this one. Never mind, we do need to save values here. Yeah, I can see why they would give you different wire colors. And that would probably make this easier to look at. Anyway, another 3-bit decoder. Where we select output for once. And then just save locations in registers. I mean, turning it around would have probably been good. Fair, 7 should read from input. So 7 should also control output, input and input. And this one should work out fine then. Though that also means I do have to take that apart real quick. Because this one will go to output then. Yes, Windows, I get it. It's a really bad day for you. So 1, 2, 3, 4, 5, and 6. And 6 ones over here to select save location. Now. Where? Ah, over here. Do you want to tell me why? Component factory. This one probably. If we have an 8. We are indeed just outputting there. Inputting from there. Yeah, whatever. Okay, we get an 8 here. Yeah, shouldn't be a problem. Should it be a problem? Well. We do have one of those, so let's tear that part down and build another beautiful one. Actually, I do want my input. Okay, 0 is the opcode for our algorithmic unit, which we have in custom components. Great. Now this one chooses input. Can I actually look it up in instruction? No. No, I cannot. Add opcode for input, and that's basically it. Let's move all of that bar over here. Get a decode, get a splitter over here. And another splitter. and 2 decoders too. And I am getting interrupted for a second. Okay, I am back again. Let's do, however, use a few OR gates still. They are over here. One of them, 2, 3, 4, 5, 6, and 7. Let's also connect this one. And connect our registers as well. Fine, if you want to do ugly wiring game, please do. Now we do have those connected. However, I do also need a bunch of 8-bit switches. And let's pick another color for that. Connect them real nice. Do the same over here. Next, choose another line. Remove all of those because I did it wrong. One, 2, 3, 4, and 7. Now we can select this one and connect this to here and here. Well, at least it will be a very colorful mess this time. Now that's a common data line. And this one will be as well. Going over here. And then we will need another byte splitter. And a decoder. Gray wires again. Let's pick this color for our save and load operations. And the last one for output. And we will need another few of those. Those can all be connected back here. And then we choose this color again. And connect the output to the corresponding registers. And of course output. Yes, we do have input as both of them. Though the ALU should do an addition, shouldn't it? In that case, let's go to component factory and take a look at what the ALU isn't doing. Now we do have a 0 over here. I see. Well, okay. Let's build our own then. Which means we will need another decoder here. Split here. Gray wire up there. And in this case, we need math 1 addition. just to keep the pattern, we will do our switch right here. Okay, input A, one input, another input, 16 to register 0. Register 0 input. Why does it have 24 now? This should now select register 1, shouldn't it? Ah. Yeah, I do need to connect the wire for it to work though. Why that? 20, 24. Add 24. Well, yeah, after 28 after 24 it should actually be 28. I mean, I can technically fix it, but I shouldn't have to. What does this tell me? Yeah, whatever. Register 0 to 5 to... yes. 0, 1, 2, 3, 4, 5. Counter to 6, output to 7. Continue. Yes. Okay, we have 4. Then we go to 8. Then to 12. 16, yes. 20, 24. Not 20. Counter is a result address. Okay. Well, in that case, this will be very Not nice to see again. I mean, the level name is not entirely wrong, is it? It is technically wire spaghetti. Implement add, subtract, and or not XOR. Okay, yeah, easy enough. So we do have add, we will have subtract. Which will basically use an add and a negation. And another switch, of course. 8-bit one, though. And or not exclusive or. Which means and or not and exclusive or will be easy enough. Let's just continue with wire spaghetti. Yeah, no clue what's going on, but well. That should do it. Opcodes implemented, nice. Sometimes it used. Yes, we are used to that. I mean, easy enough, I guess. Let's pull this back a bit. Uh, 7 to arc 1, right? No, 7 to arc 2. Let's pick green, I guess. This one disconnects that. This one disconnects that. And because we can, I guess, we will move that over here and this one down here. Get 2 more switches. Connect this one down here. This one up here. And this should work out fine. No. We do not have... We should not have anyone active over here. Never mind, I have connected the wrong wires. This one will go down here. Yeah, let me... disconnect. It shouldn't be able to. Ah, because I need to connect it over here first, of course. Wrong one again though. And this will also go down here, and this will also go up here. And if we connect the right wires, it's actually working just fine. Onwards. Add if statements to your circuit. No, I don't think that's a good idea. Well, sure. $32, $33, $30. I mean, sure, I can, I guess. Let's first disable this one if we have one of those. Get another decoder. And here we can do that. And the last one is a jump address. Which means we will have to use a switch here. Great. And another switch here. And we can implement an OR gate there, but first off, if we have a connection on this one, we will enable this one. And override we'll get a nice OR gate, I guess. Now we do need to read through it again. If equal, if not equal, less or equal, greater or equal. Basically what we're used to already. Equal, I will be able to take those two data lanes again. Easy enough. Equal, not equal. Unsigned. Do I have a greater than? No, I have a smaller than. But I can't just switch them, can't I? And of course a few more knots. Here and here. Those two, and those two, but switched. And then we need a few switches. 1, 2, 3, 4, 5, and 6. And also connect those up real nice. If equal, if not equal. If A less than B. That should be pretty much it. And that one will be needed all the way over here. Does it work? If equal. Okay, yeah. If not equal, jump to 0. They are equal. So this is false. Next one, add. If equal, we do get 1 and 0, which is not equal. So we will get a false. Fair enough. Okay, if rec 0 equals rec 2, register 0 equals register 2. Jump to 16, it shouldn't do anything. If equal 1 to 0, it should also do nothing. If this equals that, of course. $24, we should get a 24 here. Yeah, we do have this one, which goes all the way over here. Yeah, of course. Yeah, connecting the right lines does help a lot. No, please do. Well, this is a huge mess. Okay, that's easy enough, yeah. Yes, first 1 and then 4. C, a 7, 9, 1 and B, what was B? This. And a 32 is a 3 and a 2. 17 is a 1 and a 7. 2. Fair enough. Hexadecimal. Basically the trick is you can split it here, and this one it was 2. This one would be 8. Those all correspond to the most significant thing here, and those will represent the second one. Makes it easy enough to convert. Let's see, what do we have to do here? To shift a value 1 left, you just, yeah, we will use shift left logically. Windows just crashed the game. I will be right back. We are back again. Shift a value by 1, yes. Okay. I mean, there are really two ways to do this, and as usual, I will choose the one that is really just the worst possible way to do it. Actually, let me do it at least a little bit easier on myself. Actually, this was entirely the wrong direction, which is, well, unfortunate to say the least. Was it? Yes, it was. Well, let me change that real quick. I am doing it the wrong way around again, which I would really not recommend. And that's really unfortunate. Let me... Okay, 8, so we connect to 16 now. And 32. 64 and of course 128. Now there are most likely way better ways to do this. However, we just chose one that is really quick and dirty to do. Which is now just doing a bit of a lot of switches here. And then we will take this one apart. And just lazily add a decoder right here. Let's take another color to make it at least a little bit easier on the eyes. And that should pretty much be it. It was correct the first time around, okay. Okay, shift to the left. No, it should have been right. No, I don't want to write a comment. Please don't make me. No, I'm pretty sure this is still one of the most terrible ways to do it, but it is working and quite easy to build. It is, however, still the wrong way around, so... yeah. Take that with a grain of salt. In that case, we will just mirror it real quick. I still wired it the wrong way though, so it still won't work. Well, learning experiences can be hard if you just don't want to learn. At least I built like literally every other version of this you could. So we will probably need to build them again in a second. You shouldn't get 20 now. You should be able to just input 6 there. No, because I'm stupid, okay. Well. It is time to rewire it again. Let's choose colors for this one though. So at least it can be a very colorful mess. This actually doesn't make it easier to look at all. Well, at least I tried. Great, thanks for letting him do it. Thanks a lot. I mean, those are 4-bit numbers, that's pretty nice. Shift left I want. Do we have... Yes, we do have 8-bit shift left. Now let's get a constant of 1. Easy enough. Next we do want to make a bit. Actually I do only need 3 of them. We do however also need a few switches real quick. Because I am doing this the lazy way again. And let's get a few additions too. And 1, 2, 3, 4. One, 2, 3, and 4. Yeah. Should work out alright. And we're done. Thanks for scaling it up. I already did it very lazily again. Okay, divide two numbers to find the quote. Please don't. Actually, I can. Do I have my instructions here? Yes. Okay. Do we have... No, we do not. In that case, this will take a second longer. First off... we probably do get... Do we get an input? Can I get an input? Yes. Okay, let's... Yeah, sure. Crash again. Okay, but where do I get my numbers, though? We do have I do of course need to enable input first. So we do have a 0. Zero, 8. Let's take 1. And another 0, I guess. Or is a... Yeah, I should have probably remembered the codes. Yes, Windows, I know you are not amazed by this. Okay, source. Seven, my mistake. Takes a 10 to register 1. Okay. Label loop. Fair enough. Now to subtract, we do need to tell our logic unit. 2 maybe? Do we get a 2? No, I do need a 1 to add. 1 to subtract, yes. And we take 1 and 2 and store in 1. So in this case we should now get 1 decremented by 3, yes. Yeah, luckily I remembered how the CPU works. Let me also reduce volume a bit again. Now, because we don't actually force ourselves to what did I do to load immediate value? Let me see. Ah, yes, of course. Yeah, we do also need to get 64. Then we will no, that's the second one. 128 0. Doesn't matter. And register 4. Let's actually take a 26 to see if I did it correctly. Yes, I did. That's just cleanup though. We do now add to register 4 a 1 and store it in register 4 again. For that, however, I do need to add a 64, so we are at a 65. 64 because 0 is addition. Nice. Next, we do need to compare register through to 0. And the last one will be our jump address. Yes, game, I know Windows is struggling to keep up. So we will need 32. And we will add 3, so we get to 35. I think. Yes. Actually, we will add 2. And we will also add 128. Compare register, what is it, 1 to 0 and jump to loop if it is. That's probably the wrong way around though. Yes, it is. . Now, which one do we have selected? This one right now, which is it actually the correct one? No, I do need to increase it by 1. Now we do have that one selected. That means I 61. Four. I should have maybe just memorized that, but now we jump back to loop. Now it does have 3. Okay, let's see, we do have 10 here, 3 here, 7 and 1. My mistake, we do add 1 to 64 is this one. Which means we disable one of them. 4 will however get saved and get the value from blue one, which should add 1 and 0 this time. No, it shouldn't. So we do use a 64 as an opcode, which means this is on, and sends a deactivation signal to this one. We will however get as our first one this one, which is a 1. And our other line should also be a 1 actually. Did I switch them around? Yeah, I think I did. No, I did not. Let me see. 1 is subtract, we take register 1, we take register 2 and save in 1, yes. First off, we load into register 1, we load into register 2. Let's take 0 and 1 for ease of use. We do have 10, we should not have 13. Why do we have 13? Because it takes. Because of course I do need to add 64. And now I can safely store in 0 and 1. Then I overwrite number 4 with a number of my choosing. $128 should however really only... yeah, of course. Plus 64 is 192. Now we load correctly into 4. Then we subtract correctly over here. Do we? Give me a second. Subtract 1 and 0 minus 1 is 7. Then we add 1 to 4. And 164. What's the problem? 32. We do have 32 for the test here. We do also need... I should have really designed this in a better way. 5, I guess. It's done 36. Let's use 36 right now. If it is not smaller than 0. $37. Now we are at that problem again where I really haven't made my life easy by wiring it this way. Now if it is not smaller than 0, never mind, this one was switched, wasn't it? This is a smaller b. So we need this one, which is 3, which means we have to add a 2 to 32, which is 34. Which gives us a jump address, and I'm however really not doing anything with register 4. Why is it resetting? What if I take register 3 instead? Should do the same actually. Yeah. Okay, I'm just doing something with register 4. Ten, 3, we do get 7, 4, 1. Actually, we should be... We are comparing 1 to 0, so if 1 is greater than 0, let's see, 64. The first one is our register. No, we do need 192. Let's add 100 to register 5 to signal we are out of the loop. Actually, we add a lot, 100 to that register twice. Now we do output this one and this one in that order. Which is, if we take a look at our unit here, zero, three, actually it is, let's say 128, 0, 3 and 7. And the other one is in number 0, if I remember correctly. Great. I do, however, need to change the comparison again real quick to this one, which is 4, which should be 2 more. No, not 2 more. I do need this one, I think. Which is this one, which is 3 added to 32, which should be 35. Though I'm really not too sure, I should have maybe made use of using different wires. Okay, what's our problem here? I mean, can pretty much just Let's see, 64 plus 128 plus 32 is 224. 0, 0, and 12, I guess. Okay, that's working. This will take a while. Okay, 35 should be equals, so unconditional jump. Never mind, 32 is equals. Never mind, we are currently here, which is b is smaller than 1. I do, however, need this one, which is 2 added to 32 is 34. Let's take this one instead, which is... Good question. 2 more. Okay. And subtract 1 again. I should really just check for the right one. This one is 1 smaller 2. That's not what we want. If 2 is smaller than 1, we do want this one, I think. Let's move it over here so we can see it better. There's 1, 2, 3, 4. 36, so this should be what we need. Let's see. This is false, we do not jump. Never mind, we do have 10, we do need to subtract 1. Setup, jump into loop. Now we do have 1 and 2, and this is getting a signal. I can try this one too though. Which is the last one. I mean, I know it is just this condition, but working in numbers makes this just a little bit annoying. Okay, I'm selecting this one. Which means if... Okay, let's think about it again from the start. I mean, at least the algorithm itself is working properly. So if B is greater than A, or if A of course is smaller than B, which is this one, 5 I think. Okay, we do now have 2 and 1. Two is technically A. Let's switch them again, I guess. Yes, Windows, I get it. You are upset today. Do have that right now, so we use immediate values. In this case 0 and 0. We are also going to the comparator, doing a jump instruction and jumping to 12. Hopefully. Never mind, I do need to jump to 32. Yes, what did it output? Yes, but what exactly did you output? Register 0, which for some reason did contain nothing. Okay, we load in. We 0 register 3. We compare. We jump in and add 1 to and subtract 1 from 0. Yes. $255 and 1, yes. For some reason nothing, okay. Why do we have nothing if we... 200... I see, what does 220... Yeah, it shouldn't. 224 should be 128, yes, plus 64. 192, yes, plus 32. And our jump address is 32. My mistake. Actually, a mistake in the CPU. I do need a switch real quick. Actually, I don't. I just need a wire. Now it should work. Yes, it does. Divide, nice. What else do we have to do? All components have a delay, yes. Okay, yeah. Now I do need 2 more gates. And that should be it. And we do have a delay, nice. Next. Okay, so basically we will get RAM, okay. Now we will only have 4 registers now. Actually, how do I want to do this? I mean, I can pretty much just use the last one here. How do I want to address my run? Let's just build a first in, first out setup. And we actually do not need most of this. We will do this as lazily as possible. We do have input. We set this to safe value. Then give me a second. Please, game. counter, which we will increment by 4 each time. Actually, we will only increment by 1. Furthermore, we will add a 1-bit memory. Can we add one that starts as on? No. In this case, we will use an always on and an AND gate. Now let's add a comparison to a constant. $32 is our number of choice. And if they are equal, do have to use a memory. Actually, do we have a switch? No, we will build one real quick. However, this should first tick up nicely, then change to 0. And we do need an exclusive OR and 1 delay. And that over here. This one over here. And a simple not over here. Now this should work up to 32. Switch over. And output. Sadly enough though, this actually does nothing. We will have to add this to our computer later anyway. Okay, the lab. Yes, I know that very well. That's very nice. Yeah, it is a very... It is... It actually isn't a CPU anymore. It's however, very efficient. Couldn't do it with less, I think. Do I have an opcode free? Yes, I do. I mean, I can also just use this one to address memory. Can only address one memory at a time. Let's see what the other levels need me to do first. What do we want to do here? We are updating the galactic. Okay. Okay, I will actually need to use RAM for that. Let's go back to the level map and complete this one first, I think. I don't think last come first served is actually that helpful. Actually, fewer people will go. Yes, probably. Easy enough, actually. Though we won't be able to use a counter for that one. That's also very nice. Pop is basically load. Push is safe. Address is here. Actually, that's a value. And here we will need a register real quick. Actually, we don't. Actually, we do. Because we don't have easy way to change that, we will use a normal counter. Which means we will just take a register, wire it to this one. Result will just be saved. And to immediate values I think will suffice. That's at least the easiest way to do it. Which will be 1 and -1. If we pop, we reduce by 1. If we push, we don't. And our adder output is the address. And because I think it will help a bit, don't we have a delay circuit? Well, let's build our own real quick. Or just use this one. Push, yes, push. Then we need to pop. Okay, in that case, let's build it better. This is our address. And if we pop, we will reduce by 1 and save. And if we push, we will increase by 1 and save. Actually, let's just make this needlessly more complex. And I am getting interrupted again. Okay, I'm back. Now let's do 2 switches again, 8-bit. Pop means load, okay. Actually, it really doesn't have any way to work if I don't actually connect output, does it? And the game crashed again. Well, let's get back to it. And obviously we should connect this to output 2. And two constants, -1 and 1. Now if we want to push, we will increment it. I do also need an OR. Yes, Windows, I know you are very angry today. Okay, push increases. And load I want to do all the time. And that's actually input for an adder. Which we find here. And I do also need to connect one. And I should also keep 2 addresses. Okay, got it. In that case I can just use 2 counters. This one will work like that. They will be connected to each other like that. This one will count down, so it will get connected to this one. And then we just need to get a switch in front of each of those. Okay, so one of them counts up, yes. Then let's connect this one here. So what's happening now? We store one value, yes. Store the second one. Okay, let's do it another way then. Okay, 1, yes. We are at 4. We did go down to 3. I don't know why we are at 0 yet. Ah. Do nothing, okay. Okay, I see. Of course I need to stop it from doing that. Well, in that case, let's get 2 more switches in. This one will be connected back to our usual pop button. And this one will be connected to not and. Not and, no, or. Nor is what I need. And this one will basically become a not push to. Great, seems like it works alright. Well, that seems like a lot of work. How many levels do we have left anyway? Not too many. Well, I will, however, end it here for today anyway. Thanks for watching. Welcome. Not welcome. Come back next time. This is about it.